with properties of the early Earth, but we will also begin to explore the possibilities for life and branch as far as synthetic biology. So, without taking more time, let me introduce our first speaker, named Tosca from University of Cambridge.
Thanks very much, and thank you to the organizers of the meeting for inviting me to speak. This is a topic that sort of builds off of an aspect of what David talked about earlier today. This is very much a geochemistry talk, but hopefully I've provided enough context where a broader audience can follow along. Before I launch into it though, I'd like to thank, like the speakers before me did, some really excellent colleagues of mine that have been involved in this work, both from the experimental and theoretical end, but then also conceptually and pushing us to think outside the box in terms of phosphate chemistry and its implications for the early Earth. Okay, so many of us in the audience will know that phosphate plays a very important role in the origins of life, at least we think it might, and also in prebiotic synthesis. And there are really two main reasons for making that statement. One comes from the deep-rooted and diverse functions that phosphate plays in modern biochemistry, and that's led scientists over the years to hypothesize that phosphate must have become involved in biochemistry relatively early in the process. The second reason for making that statement is because we now understand over the last several years of work coming out of organic synthesis laboratories that phosphate plays a variety of roles in mediating key steps towards the synthesis of important biomolecules. And so for those two reasons alone, phosphate is actually quite important to the story, and so is its availability in different environments. Now, as David alluded to earlier today, most natural waters on Earth are actually quite low in phosphate. And the problem is mainly because of cations, so that is divalent cations, calcium and magnesium to a lesser extent, then also iron if we're going to consider environments on the early Earth. And this is a diagram that sort of maps out theoretically the solubility of different phosphate minerals. So the solubility of minerals is basically indicated in the white regions where the mineral will precipitate, and then these curves indicate basically the highest amounts of phosphate that you can get in a system controlled by one of these phosphate minerals. Now, as David mentioned, some important results have come out of this group pointing out that some waters on the modern Earth are quite phosphate-rich, and there are very good reasons for this, and that's because carbonate-rich environments, for example, Mono Lake, that tend to precipitate large quantities of calcium carbonate, do so to the point where they remove the only important divalent cation, calcium, out of the equation. And then once that step is basically completed, the phosphate that's left behind in the lake is free to increase in concentration. And so in a rather extraordinary study, Toner and Kathleen pointed out that these lakes tend to be associated with very high phosphate concentrations, which make them relevant and attractive environments regarding prebiotic synthesis. But if we're considering environments on the early Earth, we should also take note of the fact that available constraints suggest that the Archean atmosphere, and by extension the earlier Hadean atmosphere, were likely characterized by very low concentrations of atmospheric oxygen. And so what that implies is that iron was potentially an important component of the story. And it will probably surprise you to learn that we don't really understand all that much about iron chemistry regarding natural waters on Earth, that is, iron in the reduced state, ferrous iron. And part of that reason is because today's atmosphere has high concentrations of oxygen, which basically preclude significant concentrations of dissolved Fe2+. But it turns out that there are large concentrations of sediments that were derived from marine environments that are extraordinarily rich in iron. The best known among these would be the famous banded iron formation deposits, which really peak in their abundance at about 2.5 to 2.7 billion years ago. Now those sediments adorn the covers of textbooks, and their classic appearance is actually bright red. And actually turns out that the reason why they were red is because they reacted with oxygen far later, or a long time after the initial time that they were deposited. We understand that now, and that's a relatively recent revelation that's come out of the last several years of high-resolution microscopy, really probing at the finest details of what's really making up this sediment, what the original sediments were. And you can see that this is, these are core photos of banded iron formation sediments that are actually green in appearance, and they're green because they're highly concentrated in ferrous iron. And so the emerging picture of the early ocean, at least in the Archean, is that there were significant quantities of ferrous iron around, enough to precipitate minerals like ferrous iron silicates, for example, which we've spent time studying in the laboratory. And in fact, my group has spent a fair amount of time working out the chemistry of seawater and understanding how that chemistry has evolved over time. And iron ends up being a really important part of that equation. For a long time, though, considering phosphate chemistry, it was thought that ferrous iron was actually quite a problem for phosphate. And this is basically the reason why. It's because if you have ferrous iron in solution, that ferrous iron will tend to combine with the phosphate that's available and form this gorgeous blue-looking mineral called vivianite, which is a ferrous iron phosphate mineral. It turns out that vivianite, or at least the data that were in literature until recently, suggests that vivianite's incredibly insoluble. And so the thinking and the interpretation of the data that were in literature is that, well, if ferrous iron and phosphate were in solution together, the phosphate would be scrubbed up, and that would basically, vivianite would act as the lid on phosphate concentrations and basically preclude significant amounts of phosphate in anoxic waters. We became interested in exploring this problem mainly because there are environments on the modern Earth where ferrous iron and phosphate reach appreciable concentrations. And those environments happen to be at the bottom of the Baltic Sea and some other marine environments. So if you go to the bottom of the Baltic Sea and analyze the waters in which the sediments are bathed, so those would be sediment pore waters, it turns out that those pore waters have relatively high concentrations of ferrous iron and phosphate, and they crystallize the mineral vivianite. And so when we looked at these concentrations, we thought that something was wrong, or at least discrepant, in our understanding of the solubility of ferrous phosphate and what we could see from the chemistry of pore waters coming out of modern marine environments. And indeed, if you look at the data in which solubility was collected experimentally, it turns out to be a relatively restricted pH range. It was never determined for complex electrolytes like seawater, and so we thought that was worth investigating. So what we ended up doing is measuring iron phosphate solubility in anoxic seawater, so that's seawater that has absolutely no oxygen. We do this with glove boxes in the laboratory. And measure the solubility of this mineral as a function of pH, ionic strength, which is a measure of how concentrated the water is, because we don't really have a good idea of the ionic strength of seawater on the early Earth. And we took all of this information and we folded it into a chemical model that allows us to predict phosphate concentrations and solubility across a much broader range of environmental conditions, to really test the hypothesis that phosphate was so scarce in early seawater. And so for those of you who are interested in the technical details, we did this by using a well-known thermodynamic framework for understanding electrolyte solutions. This is how that model performs relative to measurements that have actually been made in modern seawater. So these are data points where we're looking at the ratio of these element concentrations, or these species concentrations in seawater as a function of salinity. And this just shows us that our model does an excellent job of fitting observations, so it's really nicely tuned for phosphate chemistry in the seawater. But of course, this is modern seawater, and we haven't folded iron into the equation yet. And when we do that, so on the left-hand side are the raw data, the solubility measurements that we made, combined with the existing solubility measurements. When we fold iron into the model, it turns out that we need to include relatively strong aqueous complexes. So these are complexes between ferrous iron and phosphate species in water. in order to account for the solubility data. So it turns out that these phosphate complexes become very important at higher pH when protons come off of the phosphate species and allow it to interact with iron. And that's a major reason why vivianite, or iron phosphate, increases in solubility substantially with increasing pH, or at least pHs that might be relevant to seawater or other more alkaline environments. Another thing that we did, so we had the experimental data and we had our electrolyte thermodynamics model tuned for seawater. We wanted to go back and really judge how accurate we were in estimating phosphate solubility before we kind of direct the model towards phosphate chemistry of early seawater. And so we went to pore water data that were collected from the Baltic Sea, so the areas on the modern Earth that I mentioned a few slides ago. And so this is one way of depicting those data. So on the y-axis, we've got depth in the sediment, and on the x-axis, we've got the analyte concentration. So in this case, as you go deeper and deeper in the sediment, sulfate ends up getting used up because of microbial sulfate production. Methane ends up being produced. And then you can see that there are horizons outlined in gray, where total phosphate concentrations increase substantially. And then below that horizon, ferrous iron increases. And basically what you have is you have diffusion of that ferrous iron upwards to the phosphate-rich zone, where presumably waters become saturated with respect to iron phosphate. So our model calculates that below this zone, you are perfectly at equilibrium saturation with respect to vivianite. And that's good, because those are the horizons where vivianite's actually been identified in those marine sediment cores. So it means that we're doing an excellent job of predicting accurately total phosphate concentrations in iron-containing seawater, or at least derivatives of iron-containing seawater. So now that we validated the model, we decided to apply this to problems related to the early Earth, and that was met with some interesting results. So before we get into that, this is just our estimate of iron phosphate solubility as a function of pH in seawater. So this is total phosphate concentration as a function of different iron concentrations. So remember, because solubility is a product of iron and phosphate concentrations, the product of those quantities multiplied together has to be the same. So as we increase iron concentration in our seawater, correspondingly that leads to lower phosphate concentrations if we're in equilibrium with iron phosphate. But you can see that these solubilities correspond to orders of magnitude higher than previously predicted. So the previously predicted values would actually be way below this, so off of this chart. It actually turns out that there's an even more interesting effect, and that is that the solubility of all phosphate minerals increases when ferrous iron is in solution. And so this is just an example of a calculation done looking at the solubility of calcium phosphate minerals as a function of iron concentrations in solution. And so you can see that with no iron, this is our solubility of a rather important calcium phosphate mineral that we think precipitates from marine environments, oxycalcium phosphate. It later becomes apatite for reasons that are mainly kinetically controlled. But because iron complexes with phosphate so strongly, as we increase iron concentrations, the solubility of calcium phosphate increases higher and higher, and this is quite a substantial effect. So this is very interesting because it means that ferrous iron and its complexation with phosphate can actually lead to high phosphate concentrations regardless of the phosphate minerals that end up being the solubility controlling species. So the very last thing that we needed to do in order to run calculations that were appropriate to marine environments on the early Earth was consider two extra chemical components. And those include CO2 and silica, referred to here as SiO2 in the aqueous state. Both of those components are thought to be relatively enriched in seawater on the early Earth. CO2, for reasons that David went into earlier, there are various constraints that require that CO2 concentrations were much higher then than they are now. And silica is thought to be much higher in early seawater, mainly because diatoms hadn't evolved yet. In the modern sea, diatoms use silica quite efficiently, and that leads to very low concentrations of silica in modern seawater. But of course, that wasn't the case throughout the early Earth. And in fact, we recognize that this was the case because the sedimentary record indicates that silica was readily available in the ancient ocean and precipitated as a variety of silica minerals, but mainly as quartz, or referred to in the sedimentary geology context as chert. Okay, so wrapping up all of this together then, we could estimate total phosphate concentrations in seawater systems that are most appropriate for the early Earth. And so these are a number of different curves looking at phosphate concentrations as a function of pH. And you can consider these curves as basically the ceiling for how high phosphate might have been in seawater systems. There are a couple of important variables that control phosphate solubility. Obviously pH is one of them, so we don't really understand very well what the pH of the early oceans might have been, but I have some references to earlier publications that have come up with suggestions of what that might be. Another aspect of this is iron concentration, but again, we think we have a good handle on the relationships that govern iron concentration in the early oceans. But the last and potentially most important variable relates to cation composition, so the concentration of things like calcium and magnesium in early seawater. And it turns out, at least regarding the Hadean, we don't have a very good idea of what those concentrations might have been, but they do matter. And the way we handle this is we try to bracket a reasonable uncertainty in those values by considering different situations. Where seawater, for example, was very, very rich in calcium, but relatively poor in magnesium, and that would be this bottom curve. And then situations where seawater was relatively rich in both cations. And our basis for choosing these scenarios, and in fact, some of the major controls and how high calcium and magnesium might have been in early seawater really relates to how seawater gets processed through hydrothermal systems hosted at the seafloor. So the way we understand that process today is that those systems tend to scrub magnesium out of seawater and they supply a lot of calcium. And so the end result is that with increased fluxing of seawater through those systems, you might lead to a situation where you have high calcium but relatively low magnesium. It turns out that there are variables controlling that process that we really don't have a good handle on. For instance, the concentration of dissolved CO2 within those hydrothermal systems. But the curves that we've chosen here have actually been informed by experimental interaction between hot fluids and ancient mafic rocks that give us some guidance on that. In any case, one of the most important conclusions from this diagram is that the upper limit on phosphate concentrations was a few orders of magnitude higher than we previously thought. And that's potentially good news if you're thinking about the early origins of life, which I'll get into in the last slide. It actually turns out that there's some observational evidence that might suggest that we're not too far off the mark here. And so we've been working with Birger Rasmussen and colleagues at the University of Western Australia. And Birger has really led the charge in applying high-resolution transmission electron microscopy to ancient sediments. So basically using those high-resolution techniques to really explore what the original minerals were and what they tell us about ancient seawater. And it turns out that for many banded iron formations that range in age throughout much of the Archean, so approximately 3.5 to 2.5 billion years ago, nanocrystalline apatite, a calcium phosphate mineral, is pervasive and it's spread throughout those deposits. This suggests that seawater was actively making calcium phosphate chemically. And so applying our model and our experiments to these observations suggests that indeed in ancient systems that happen to be associated with large quantities of iron, so you can see also iron minerals deposited in this same sediment, provides some support for the relationships that I've spent time talking about. So just to conclude here, one interesting aspect of this is what happens if you take seawater and you evaporate it. So what the ceiling might be in terms of evaporative processes. And the thermodynamic parameters that we've extracted from our experiments allow us to do this. So what this diagram shows is phosphate concentration as a function of pH for different waters that have been concentrated through evaporation. And there are two sets of waters on this diagram. The green points are estimates of early seawater, and so when you evaporate those under different conditions of alkalinity and initial pH, which are important parameters, you can traverse a phosphate pH space that actually exhibits some pretty significant diversity. In fact, you can even pump phosphate up a few more orders of magnitude to the range where it starts to become very interesting for prebiotic synthesis. We even did this using waters relevant to the early surface of Mars as a proof of concept to show that in systems where iron is present, you could potentially do the same thing. And it turns out that if we have some reasonable constraints on what dilute waters on the Martian surface might have looked like from analyses from successful Mars exploration rovers and laboratory experiments, it turns out that there too you could potentially produce phosphate-rich waters. So I'll leave the major conclusions up on the board here, but some of the most interesting, I think, relate to the fact that our results, our experimental results in our model, suggests that seawater might have featured phosphate concentrations a few orders of magnitude higher than we previously thought. And that's interesting because it might suggest that seawater could have served as an important phosphate source to environments on the early Earth that might have come in contact with seawater. I think it's important to emphasize here that I'm sort of agnostic over the exact environment that might be best for prebiotic synthesis, but I will say that David Catling outlined some very compelling arguments for why lakes, in particular alkaline lakes, do end up solving a variety of different problems. If that's the case, then it becomes very interesting to ask how such systems might have interacted with seawater. So what are the environments that could potentially be seen as a marginal marine lake, and could we source phosphate from seawater in that way? If not, if it turns out that source of phosphate isn't required, then phosphate-rich seawater becomes interesting in the later stages of microbial evolution, once life has effectively taken off on its own. And it's interesting to think that within the seawater there resides an enormous pool of phosphate ready and waiting to support early life. So I'll leave it there and be happy to take any questions. Thank you.
Several questions I'm trying to do myself. So my first question is any way initial results would not also apply to salt lakes? And then also, are your results, could your results be dependent on DIC concentration? So could we be looking at another instantiation also, if I think beyond iron, also at about calcium, could this also be partly caused by this calcium carbonate mechanism that David Catling talked about in the morning?
Yes, absolutely. So to answer your first question, I think the results are directly applicable to saline lakes. Was that the general question? Or salt lakes? Yeah. Yeah, they are, because iron's an important part of the equation, and although the system that we've spent time applying our model to includes seawater, the data that we produced are fundamentally applicable, so it allows us to examine how iron might behave in early saline lakes that are evolving in terrestrial environments. I'll say though that alkaline lakes on the early Earth would have been saline to some degree, because if those lakes were associated with relatively alkaline conditions, or perhaps even pH values on the high side, then that requires some compensating concentration of cations. Regardless, the high salinity aspect is interesting, but this also poses a question in terms of how much of a problem could high concentrations of salts be? Because in order to tap into this phosphate from seawater, of course, all of the dissolved salts that presumably are resting in seawater anyway come with it. And I guess your other question was related to David Catling's mechanism for concentrating phosphate. Our results don't in any way negate that mechanism at all. So what they allow us to do, though, is they do allow us to account for how iron might have been behaving in those lakes. So a lot of the data that David and John Toner ended up producing were from the lakes on the modern Earth, of course, are relatively low in iron because of oxygen concentrations. But now I think we're in a better place to examine how iron might have behaved and the ways in which it could have been partitioned and its impact on the chemical evolution of those systems.
Thanks very much. Point number 4 up there is, of course, of great interest. Because let's say we have orthophosphate abundant in seawater. How do we activate it? Now, because you can have as much orthophosphate as you want in solution, and then but to phosphorylate a nucleotide. This is a problem that Stanley Miller often reminded us of. He would scratch his head and talk about some of these very rare protonated phosphates that one finds in the mineralogical record. So can you elaborate on this a little bit? Because that seems to me to be the elephant in the room.
Thanks for pointing that out. In a late version of the talk, I decided to put that bullet in as sort of a provocative point because we did the thermodynamic analysis on this, but I forgot to mention it in the last slide, so thanks for giving me the chance to talk to it. One consequence of a phosphate-rich ocean is that as seawater gets pulled through hydrothermal vents and gets heated, it will come back out again. And looking at the way phosphate behaves in modern hydrothermal vents, it turns out that phosphate isn't sequestered. It's in seawater, and it comes back out again. So hydrothermal environments, hydrothermal systems hosted in the seawater don't do much to phosphate, but they do increase temperature. And so thermodynamically, we wanted to know whether phosphate-rich seawater could potentially, once it was heated at high temperature, produce various forms of polyphosphates, and thermodynamically it's predicted. So that becomes sort of an interesting corollary. So then phosphate could potentially be a phosphate source and also a condensed phosphate source as well. So that's as much as we've delved into this problem. We'd like to do some experimental work to really probe the details of that. But that seemed like an interesting consequence of the results to us too.
Can I say one more? Yeah, because it has to do with seawater chemistry, which is, of course, intrinsically interesting. So you can pull out calcium, of course, but you can also remove calcium from rocks in a process called albitization. It happens right now at the mid-ocean ridge flanks, usually on ash deposits, where you have you remove calcium from plagioclase, you make calcium hydroxide, calcium chloride, and so on. And it is befuddled geologists because we occasionally see in ancient sediments these very calcium-poor sedimentary rocks. And they're almost certainly from hydrothermal processing and then removal of calcium. I guess the point that I wanted to make in this comment, that little background, is that there are many, many different environments where the calcium-magnesium ratio can span the experimental space that you're exploring.
Yeah, that's right. So, yeah, you can see the aqueous consequences of that albitization in modern hydrothermal fluids, right? So that's where most of the calcium that's in modern hydrothermal fluids, on-axis hydrothermal fluids, is derived. Interestingly, the water-rock ratios are so low that you actually don't need much albitization to really source a lot of calcium in the water as the water sort of permeates through the reaction zone. But you're absolutely right. In the Hadean, Archean, we start changing boundary conditions of your hydrothermal systems. You can tap into a pretty diverse calcium-magnesium ratio. Yeah.
I think probably, Paul, thank you. We should, in the interest of fairness to everyone, move to the next. Nick, thank you again.
Thank you.